Imagine building molecules,
Hmm.
not just piece by piece, atom by atom, but actually controlling their exact 3D shape, down to every little twist and turn.
Yeah, organic chemistry looks flat on paper sometimes, right? But it's really all happening in 3 dimensions. It's like molecular choreography.
Absolutely. Welcome to the Deep Dive. This is the show where we take the sources, we peel back the layers, and we try to pull out the most important bits of knowledge for you. I'm your host.
And I'm your expert. And today, our mission is basically to give you a shortcut to understanding a really crucial part of organic synthesis, diastereoselectivity.
We're diving into Chapter 33 of Clayden, Greaves, and Warren's Organic Chemistry, the second edition.
That's right, we're going deep on this one.
And specifically, we want to unpack how chemists get such precise control over the relative 3D arrangement of atoms within molecules.
We'll be hitting on mechanistic reasoning, the why behind reactions, key pathways, functional group changes, stereochemistry, obviously, and even a bit of retrosynthesis thinking backwards.
Our aim is for you to walk away with a clear grasp of the fundamental ideas without getting totally bogged down in every single detail. And always thinking about, how this stuff is actually used.
Exactly. By the end, you should have a really solid framework for understanding how chemists achieve this amazing precision and, crucially, why it matters, for drug discovery, new materials, all that stuff.
Okay, let's dive in. To really get diastereoselectivity, maybe we should quickly revisit stereoisomers from earlier chapters. Just a quick recap.
Good idea. So remember, stereoisomers have the same atoms connected in the same order, but they're arranged differently in 3D space.
Right, and we had two main types, enantiomers. Those are the non-superimposable mirror images, like your left and right hands.
And then disotereoisomers. These are stereoisomers that are not mirror images of each other. They have different shapes, but they aren't perfect reflections.
Got it. So this chapter, chapter 33, it's all about how chemists make compounds as single diastereoisomers. Right, getting just one specific arrangement out of several possibilities.
Precisely. Making single enantiomers is related, sure, but it's a different challenge we'll tackle later. Today is about diastereomers, and that brings us to a really critical distinction we need to make early on.
Okay, what's that?
Stereospecific versus stereoselective reactions. These sound similar, but they're fundamentally different in terms of control.
Right, this difference is key.
Yeah.
So stereospecific. That means the reaction mechanism itself forces a particular stereochemical outcome.
Exactly. There's no choice. The 3D arrangement of your starting material directly dictates the 3D arrangement of your product. It's built into the mechanism.
Can you give an example?
Sure. Think about SN2 reactions. They always proceed with inversion of configuration. Start with an R, you get an S. Start with an S, you get an R. It's specific.
Okay, so the mechanism leaves no other option.
Right. Or E2 eliminations. They need that anti-paraplanar arrangement, remember? So
Right.
the relative stereochemistry of the starting material determines if you get the E or Z alkene. It's specific.
What about adding bromine to alkenes? I remember that one.
Classic example. Electrophilic addition of Br2 is a stereospecific anti-addition. Start with a transalkene, you get the anti-dibromide. Start with cis, you get the sind-dibromide, which is actually a meso compound or a racemic mixture depending on substituents. But the key is the addition itself is anti. The alkene geometry locks in the product's relative stereochemistry.
So in all those cases, the reaction pathway itself defines the 3D outcome.
Exactly. Now, stereoselective reactions are different. Here, the reaction could potentially go down multiple stereochemical pathways.
But it doesn't. It chooses one.
It strongly prefers one. One pathway is just energetically much more favorable than the others. So one stereoisomer is formed much more than the others.
Okay. So it's not forced, but it's heavily biased. It creates, as the book says, additional new stereochemical value.
That's a good way to put it. So the bottom line for you is, chemists have these tools. Sometimes the reaction is locked in, stereospecific. Other times it has a strong preference, stereoselective. Both allow for control over the 3D structure.
Okay, that distinction makes sense. Now, how do chemists actually exert this control, especially in selective reactions? The book introduces the concept of procurality here.
Right. Procurality. This is important when we're creating a new stereocenter. Many diastereoselective reactions start with something flat, like a trigonal carbon in a carbonyl group, and turn it into a tetrahedral stereogenic center.
So a prochiral carbon isn't chiral yet, but it can become chiral in a reaction.
Exactly. Or think of a tetrahedral carbon that has two identical groups attached. If swapping out one of those identical groups makes it chiral, that original carbon was prochiral.
Like the central carbon in glycine. It has two hydrogens, Replace one with something else, and boom, it's chiral.
Perfect example. That CH2 in glycine is prochiral. And this idea connects back to what we learned about enantiotopic and diastereotopic groups, remember from NMR discussions?
Yeah, vaguely. Groups that look the same but behave differently.
Sort of. It applies to the faces of a molecule too. If attacking one face of a prochiral group gives you one enantiomer, and attacking the other face gives the mirror image, those faces are enantiotopic, like attacking the front or back of benzaldehyde.
Okay, but what if attacking the two faces gives you two different diastereoisomers?
Ah, then the faces are diastereotopic. And this is crucial because diastereotopic faces are chemically different. A reagent can actually tell them apart. It can preferentially attack one face over the other.
And that's the basis for stereoselectivity in these reactions. The reagent recognizing one face as being different may be less hindered or electronically more attractive.
You got it. That's where the control comes from. If the faces were identical or homotopic, you'd just get the same product attacking either side. The challenge, though, comes with flexible molecules, acyclic ones.
Right. Chapter 32 talk about rigid cyclic systems where conformations are locked, making control easier. But open chains, they flop around, right?
Right.
Free rotation.
Exactly. That rotation can average things out, making it harder to get high selectivity. So the big question is, how do you tame that flexibility? How do you control reactions in these floppy, acyclic systems?
So how do you tame them? Is there a way to make them behave?
Well, even with free rotation, molecules aren't just randomly flopping around all the time. Certain conformations are lower in energy than others. And crucially, some conformations might be more reactive than others.
Okay, so we need to figure out which shapes the molecule prefers to be in when it reacts.
Precisely. Let's take a carbonyl group with a chiral center right next to it, an alpha chiral carbonyl. The key insight is that the most important conformations, the ones most likely to react, usually place the largest group attached to that chiral center perpendicular to the plane of the CO bond.
Perpendicular. Why? To get it out of the way.
Pretty much, imagine you have large, medium, and small groups on that chiral carbon. Putting the L group perpendicular minimizes steric clashes as the nucleophile approaches the carbonyl carbon.
Okay, that makes sense. And this leads to a model.
It leads to the Falkenand model. This model helps us predict how nucleophiles will add to these alpha chiral carbonyls. The nucleophile comes in at a specific angle, the Berge-Dunitz angle, about 107 degrees.
And it takes the path of least resistance.
Yeah.
Right.
Yeah.
Avoids bumping into the big groups.
Exactly. It approaches along the least hindered trajectory. So if the largest group is pointing away, perpendicular, the nucleophile will likely come in past the smallest group.
Now, here's something interesting. The book mentioned the Curtin-Hammett principle. It's not just about the most stable shape, but the most reactive one.
Yes, this is a really important point. Sometimes a conformation might be present in only a small amount at equilibrium, but if it reacts much faster than the more stable ones, its transition state is lower in energy, and that's the pathway that determines the major product. Reactivity trumps stability sometimes.
Wow. Okay, so it's about the energy barrier to reaction, not just the energy of the starting shape.
Correct. And the Falkenand model, by considering these steric factors in the approach to the reactive conformation, gives us a mechanistic reason for the observed selectivity. It's better than just memorizing something like Cram's rule, because it explains the why. We see it work, like reducing a ketone with LyLH4 might give a 3.1 ratio of diastereomers, predictable by the model.
Okay, so Falkenand focuses on size, put the biggest group perpendicular. But what if one of the groups isn't big, but it's, say, very electronegative, like an oxygen or nitrogen atom?
Ah, good question. That changes things. Electronegative atoms introduce electronic effects that can actually override simple sterics.
How does that work?
Well, if you have an electronegative atom, X, on that alpha chiral carbon, and the CX bond is aligned perpendicular to the CO bond.
Okay, same perpendicular alignment as the large group in the simple model.
Right, but for a different reason. In this alignment, the sigma star, anti-bonding orbital of the CX bond, can overlap with the pi star, anti-bonding orbital of the carbonyl.
Orbital overlap. Okay,
Yeah.
What does that do?
It effectively creates a new combined molecular orbital that's lower in energy. This lower energy LUMO, lowest unoccupied molecular orbital, is more easily attacked by the nucleophile.
So the conformation with the electronegative group perpendicular becomes more reactive electronically, even if that group isn't the biggest.
Exactly. It lowers the activation energy for attack through that conformation, so the rule modifies. If there's a significantly electronegative atom, it tends to sit perpendicular to the carbonyl, directing the nucleophile's approach, potentially overriding the largest group rule.
Is there an example of this?
Yeah, the book mentions a synthesis step towards dolastatin, an anti-cancer agent. There's an aldol reaction with amazing selectivity, over 96.4, and it's because a bulky but also electronegative nitrogen group, NBN2, sits perpendicular, guiding the reaction, not the alkyl group, which might be sterically similar. The electronic effect wins.
Okay, so we have sterics, Felkin-Ann, and now electronics, electronegative groups. But then things can get even more complex with metals, right? Chelation control.
Oh yeah, this is where it gets really powerful and sometimes flips the selectivity completely on its head.
Flips it. How? What is chelation doing?
Chelation happens when you have a metal ion, usually a Lewis acid, that can grab on to two heteroatoms in the molecule at the same time. Typically, it's the carbonyl oxygen and another nearby atom with a lone pair, like another oxygen or a sulfur or nitrogen.
Like molecular handcuffs grabbing 2 points.
That's a great analogy. The metal ion bridges between the carbonyl oxygen and the other heteroatom. This locks the molecule into a very specific conformation.
And this LOX conformation is different from the Felkin-Ann one.
Totally different. Instead of having a group perpendicular, the chelation model forces the carbonyl oxygen and the other heteroatom to be held close together, often sort of eclipsed, clamped by the metal ion in a cyclic arrangement, usually a 5 or 6 membered ring.
Okay, so it forces a new shape. Why is that so powerful?
Several reasons. One, this chelated structure is often very stable, so it becomes the dominant conformation, and it's highly reactive because the Lewis acid metal also activates the carbonyl. Two, the nucleophile still attacks from the least hindered side.
But the least hindered side is now different because the whole molecule is held in a different shape.
Exactly. So the attack often happens on the opposite face compared to what Felkin-Ann would predict. Chelation can completely reverse the diastereoselectivity.
Wow. And does it affect how selective the reaction is?
Dramatically. Chelation control often leads to much higher selectivity, frequently better than 95.5, and it usually makes the reaction go faster, too. It's like forcing the molecule into the perfect posture for a highly specific reaction.
Can you give an example where this reversal happens?
Sure, the book shows a beta-hydroxy ketone. Reduce it with something like LyLH4, you get one diastereomer via Felkin-Ann, but use a chelating reagent like ZnBH42, the zinc chelates between the hydroxyl oxygen and the carbonyl oxygen, locks it, and you get the opposite diastereomer, often with much higher preference.
And the Lutz reduction uses cerium-3, right? That also involves chelation.
Yes, adding sickle-3 to NABH4 reductions of alpha heteroatom ketones can switch the selectivity again, thought to involve a chelated intermediate guiding the hydride delivery. Size of protecting groups can also matter. If a protecting group is too bulky, it can prevent chelation, and the reaction might revert back to Felkin-Ann control.
Okay, this gives us a sort of decision tree then. When you see an alpha chiral carbonyl.
Right. First ask, is there a heteroatom at the chiral center? If no, probably simple Felkin-Ann, biggest group perpendicular.
If yes, then ask, is there a metal ion that can chelate?
If no chelating metal, use the modified Felkin-Ann electronegative group perpendicular.
But if there's a heteroatom and a chelating metal?
Then you use the chelation model. Assume the metal clamps the carbonyl O and the heteroatom together and predict attack on the less hindered face of that conformation.
That's a really useful framework. Okay, so that covers carbonyls pretty well. What about controlling stereochemistry in reactions of alkenes, especially acyclic ones?
Similar principles apply. If an alkene has a chiral center nearby, its two faces become diastereotopic. Reactions like epoxidation or hydroboration will be selective. The key here is understanding the alkene's preferred conformation.
Is there a model for that, like Felkin-Ann?
There is, based on work by K.N. Hook. His calculations showed that low-energy conformations of chiral alkenes tend to have one of the substituents on the chiral center eclipsing the double bond.
Eclipsing. Does that usually mean high energy?
Not necessarily here, but the really important factor is if there's a cis substituent on the double bond itself relative to the chiral center.
Okay, a cis group on the alkene. What does that do?
It introduces something called allelic strain, or A13 strain. It's a steric clash between the cis-alkene substituent and the groups on the adjacent chiral center. To avoid this clash, the molecule strongly prefers a conformation where the smallest group on the chiral center, usually hydrogen, eclipses the double bond.
So the cis group basically forces the molecule into having only one main low-energy reactive conformation.
Exactly. And if there's only one dominant conformation, Attacking the less hindered face of that conformation leads to very high diastereoselectivity.
Like the epoxidation example.
Yeah.
With a cis substituent, it's 95% selective.
Right, because the MCPBA just attacks the open face of that single preferred shape. Take away the cis substituent, now maybe two conformations are similarly stable, the selectivity drops maybe to like 60.40 because attack happens on both.
And can nearby groups direct reactions here too? Like the hydroxyl directing epoxidation?
Absolutely. Just like with carbonyls, an allylic alcohol's OH group can hydrogen bond to the epoxidizing agent, delivering it specifically to one face, giving excellent control.
Okay, makes sense. What about enolates? They have double bonds too.
Good connection. When you make an enolate from, say, a ketone that has a chiral center beta to the carbonyl, that chiral center is now alpha to the enolate double bond.
Right, so it's like the chiral alkene situation.
Pretty much. The enolate often behaves like a cis-substituted alkene due to the geometry around the metal counterion. When an electrophile like methyl iodide comes in, it attacks the less hindered face, usually opposite the biggest group on that chiral center.
And bigger groups lead to better selectivity.
Generally, yes. More steric bulk provides clearer differentiation between the two faces.
Now, aldol reactions. Those seem really important for building complexity, creating potentially two new stereocenters at once. How do we control that?
Aldol reactions are a cornerstone, and yes, controlling the relative stereochemistry of those two new centers is crucial. The key predictive tool here comes from the Zimmermann-Traxler model.
Zimmermann-Traxler, what's the main takeaway?
The golden rule derived from it is incredibly useful. Cis-enolates tend to give syn-aldol products, and trans-enolates tend to give anti-aldol products. It's a surprisingly reliable guide.
Cis gives syn, trans gives anti. Why? What's the model say?
It proposes that the reaction goes through a chair-like, six-membered cyclic transition state. Imagine the metal counterion, maybe lithium or boron, coordinating to both the enolate oxygen and the incoming aldehyde oxygen.
A chair transition state.
Yeah.
Okay.
Yeah.
How does that lead to synanty control?
In that chair, the substituents have to go somewhere. The substituent already on the enolate that makes it cis or trans gets forced into either a pseudoaxial position, if the enolate was cis, or a pseudoequatorial position, if the enolate was trans. Then the group attached to the aldehyde, let's call it R, generally prefers to sit pseudoequatorial to minimize steric clashes within that chair. The combination of where the enolate substituent has to go and where the aldehyde substituent wants to go dictates the relative arrangement of the two new stereocenters, syn or anti.
So the geometry of the enolate, cis or trans, sets up the transition state chair, which then determines the product stereochemistry.
That's the essence of it. And the really neat part is that chemists have learned how to control the enolization step itself to selectively make either the cis or the trans enolate.
Ah, so you control the enolate, and the enolate controls the aldol outcome. How do you control the enolate?
For simple ketone lithium enolates, the size of the group on the other side of the carbonyl matters. Bulky groups tend to favor making the cis, or Z, enolate. But boron enolates offer much more precise control.
Boron. How did that work?
By choosing the ligands on the boron region. Use bulky ligands like dicyclohexaboron chloride, CHEX2BCl, and you strongly favor formation of the trans E enolate. That then goes on to give the anti-aldol product.
Okay, bulky boron gives transenolate, gives anti-aldol.
Right. Now, use less bulky boron regions, like 9-BBNOTF or dibutyl boron triflate, Bu2BOTF, and you selectively get the cis-Z enolate.
Cis enolate gives
the syn-aldol product. So by simply choosing your boron region, you have a switch to dictate whether you get the syn or the anti-aldol diastereomer. It's incredibly powerful for synthesis.
That's fantastic control. So all these methods, Felkenan, chelation, Hook, Zimmermann-Traxler, they let us make specific diastereoisomers. But often, especially in medicine, you need one specific enantiomer. How do we get there?
That's the ultimate goal, often. And the key link is the starting material. If you start with a racemic mixture, even the best diastereoselective reaction will just give you a racemic mixture of products. Two diastereomers, but each one is 50.50 R and S.
But if you start with something that's already enantiomerically pure...
then any diastereoselective reaction you do will produce an enantiomerically pure product. You're essentially transferring the initial chirality through the sequence, controlling the relative setup of new chiral centers.
And this is where the chiral pool comes in.
Exactly. The chiral pool is like nature's gift to organic chemists. It's the collection of readily available, cheap, enantiomerically pure compounds that nature makes things like amino acids, L-serine, L-isoleucine, sugars, glucose, terpenes, limon.
So the strategy is start with one pure enantiomer from the pool.
And then use all these clever diastereoselective reactions we've just talked about to build out the rest of the molecule, adding new chiral centers with defined relative stereochemistry.
And because the first center had a known absolute configuration, R or S, and all the new ones are set relative to it, you automatically define the absolute configuration of the entire molecule.
You've got it. It's a hugely important strategy. You only need one chiral starting point from nature.
The book gives a great example. Methylmicaminoside, a sugar with 5 chiral centers.
Yeah, complex molecule. But the synthesis starts with just one chiral center from the pool, S, lactic acid. All the other 4 chiral centers are installed using diastereoselective reactions, a cyclization where a methyl group has to go equatorial, a ketone reduction where hydride attacks axially, a hydroxyl-directed epoxidation that sets up 2 centers, and an epoxide opening with inversion, step-by-step control, starting from one chiral seed.
That's really elegant. And then there was the Penaracid A story, proving the structure.
Oh, that's a fantastic example of synthesis being used not just to make something, but to figure out its exact 3D structure. It's a natural product from a sponge, structure mostly known, but the overall absolute and relative stereochemistry was uncertain.
So they had to synthesize the possibilities to see which one matched.
Exactly. K. Mori and others synthesized potential diastereoisomers using carefully controlled stereoselective steps, starting from chiral pool amino acids like L-serine and L-isoleucine.
And it wasn't straightforward, right? They ran into problems.
They did. For one part, a planned directed epoxidation actually gave the wrong stereochemistry. They had to block the directing hydroxyl group with a bulky silly group, TBDMS, to force the epoxidation agent to attack the other face. Clever problem solving.
And another step involved an unusual reaction of an amino acid, diacetization, that happened with retention of stereochemistry.
Yeah, via a strained intermediate, an alpha-lactone. Not the usual outcome, but crucial for getting the right building block. And then linking the two halves together, even the geometry of the alkene used for coupling mattered. Using an anti-version gave the wrong final product. They had to specifically make and use the syn alkene.
So, piece by piece, using highly selective reactions, they built the molecule until it perfectly matched the natural sample.
Right. And the big takeaway there is powerful. Sometimes, even with all our modern spectroscopy, the only way to be absolutely sure about a complex molecule's detailed 3D structure is to synthesize it unequivocally. Synthesis as the ultimate proof.
Wow. Okay, what a deep dive that was. We've covered a huge amount from stereospecific versus stereoselective, prochiral centers, the Falcon-Am model, and its electronic modifications.
The power of chelation control to flip selectivity, controlling alkenes with the Hook model and allylic strain, taming aldol reactions with Zimmermann-Traxler and boron enolates.
And finally, how all of this connects to making single enantiomers using the chiral pool, even using synthesis itself to determine structure.
It's really about building molecules with intention, controlling that third dimension.
And the aha moment, I think, is realizing this isn't just theoretical chemistry. Controlling 3D shape is absolutely fundamental. It's how drugs fit into receptors, how enzymes work, how materials get their properties.
Life itself is incredibly stereoselective. Precise 3D recognition is happening constantly in our bodies.
Which leads to a thought to leave you with. As you go about your day, consider all the molecular interactions happening inside you, many likely governed by these very principles. What other biological processes might depend on this kind of intricate 3D control in ways we haven't even discovered yet?
Something to ponder. This is really just scratching the surface of asymmetric synthesis. There are even more advanced methods building on these ideas that we might explore in the future.
For now, though, that brings us to the end of this deep dive.
Thank you for being part of the Deep Dive family.